Hello, sir.
Yes.
Okay, I just wanted to know if we are back on.
Sorry?
Just wanted to know if it is back on or is not like talking.
Okay, yeah, we're back. Okay. So the first classification, we say on the basis of structure, we have an amino acid that have a side chain that is aliphatic in nature. And we know what is an aliphatic as opposed to aromatic, right? So we have about five classes. We have about 5 amino acids that fall within this class. We have the simplest amino acid, which I said glycine. And you can see the structure. We can see the 1-letter code, the 3-letter code, and then the structure of the amino acid, and then the distinct group within the side chain. All this. Can you mute yourself? Can you mute yourself, please? Good. So we said the simplest is glycine. And we said this glycine, how it differs from the basic unit of all the amino acids is that the the R group or the side chain is just a hydrogen. So you can see all the side chain here from the structure in red. So how it differs from the basic structure of all the amino acids is that the R chain is just a hydrogen. So we've seen it in glycine. That is why we say when you look at the alpha carbon of glycine, it contains 2 hydrogens that made that carbon not to be considered as acyclic or carbon, which is different with regard to the next amino acid, alanine. In alanine, what we have is a methyl group. So a methyl group is attached to the alpha carbon, which is now the beta carbon. Lysine and alanine differ in this group with the rest because the rest have a branch chain. In Berlin, you have the beta carbon attached to 2 methyl groups in a branch form. So you have the branch forming on the beta carbon. While in leucine, you have the branch forming on the gamma carbon instead of the beta carbon as in the case of beryllium. While in isoleucine, the branch still maintained in the beta carbon, but one of the branches is longer than beryllium because of what? Because one of the branches has 2 carbon, 2 methyl groups, while one of the chain is only 1 methyl group. So when you look at beryllium and isoleucine, the difference is that, yes, the branch is formed on the beta carbon, but one branch is longer in terms of the number of carbons than the other. Is that clear? Essien? 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 Are we together? Class, are you together?
Yes, sir.
Yes, sir.
Okay. So basically under this, The R group is basically an aliphatic group. But we have a simpler ones, which we say the glycine and alanine, and we can see the R group is just a hydrogen and then a methyl group. While in the case of valine, the R group, in the case of valine, leucine, and isoleucine, the R group are in form of branch, where we have methyl group attached to beta carbon in the case of valine, and then another methyl group attached to gamma carbon in the case of leucine, and then we have this methyl group attached to beta carbon, but one of the branch is one carbon longer than as in the case of valine. Is that clear? So the next is hydroxyl group containing amino acids. So amino acids, they contain hydroxyl group. The first one here is serine. When you look at the structure of serine and remember the structure of alanine, you will see that the alanine only have a beta carbon, which is the methyl group. Now just imagine that beta carbon methyl group substituted in one of the amino acids with a hydroxyl group. You're going to have what we call serine. So on the beta carbon, you have a hydroxyl group. This gives what we call serine. Is that clear? In threonine, you have two carbon attached to the alpha carbon. On the beta carbon, you have a substitute of hydroxyl group. Gives what we call threonine. And then the last one is tyrosine. Tyrosine contains the group containing the basics group, which is the carboxyl group, the amino group, the hydrogen, all attached to the alpha carbon. And then you have an aromatic ring. On that aromatic ring, you have hydroxyl group attached to it. Just imagine you have a, benzene ring, right? We know benzene ring, right? Class, we know benzene ring. Do we know benzene ring? Are we here?
Are using data to watch all those things, right?
Class, are we together?
Yes, sir.
You should be responding now. We know benzene ring.
Yes, sir.
Good, Alec. So, what happened in the case of tyrosine is you have a benzene ring attached to a hydroxyl group. And when we have a hydroxyl group attached to benzene ring, what do we call it? We call it phenol, right? So you have a phenol group attached to the alpha carbon, and that is called tyrosine. And we'll still see tyrosine under aromatic amino acids because it has the benzene ring with an OH group. So it can be under amino acid with hydroxyl group or also amino acid with an aromatic ring. That is why here the structure wasn't depicted. You see it better. Now, the next class is sulfur-containing amino acids. In sulfur-containing amino acids, we have the R group containing sulfur atom. So the first one is cysteine. In cysteine, you have the beta carbon attached to a sulfur-hydryl group, just like we mentioned serine, where the beta carbon is attached to hydroxyl group. But this one, the beta carbon is attached to sulfur-hydryl group to give what we call cysteine. We have this cysteine, but you can see it is not listed as number 9. Cysteine is when you have 2 cysteine. But basically, this is a modification, a modified form of cysteine. You can have cysteine in a protein. During protein folding, you can have 2 of these cysteine coming together. The sulfur-hydryl group can come together to form a bond between the 2 sulfur atoms to give what we call a disulfide bridge. We'll see what is disulfide bridge and to what importance is disulfide bridge. Disulfide bridge is very important when we are talking about the formation of secondary and the tertiary structure and a protein. Then the next one, we have methionine. In the methionine, we have the beta carbon, the gamma carbon, and the lambda carbon. Between the gamma carbon and the lambda carbon, they were attached to each other by thioether group. And this thioether containing the, in fact, that's why we call it's an ether linkage, but in this case, not oxygen. We have a sulfur. That is why we call it thioether linkage. And that is methionine. The next classification is acid amino acid and their amides. What are these acid amino acids? These acid amino acids, you have the basic groups in an amino acid, which contain the carboxyl group, the amino group, hydrogen, and then the R group. Remember this, the first carboxyl group, we call it the primary carboxyl group. So any carboxyl group that may occur in any of the R group is the secondary carboxyl group. So what happened in the case of aspartic acid? You have on the alpha carbon another methyl group which form the beta carbon. On the beta carbon, you have a carboxyl group attached to the beta carbon. So you also look at the structure of serine, where we say OH is added. You look at the structure of cysteine, where we say the sulfur-hydryl group is attached to the beta carbon, while in the case of aspartic acid, we have a carboxyl group attached to the beta carbon. The same thing in the case of glutamic acid, where we have another carboxyl group, but in this case attached not to beta carbon, but rather to gamma carbon. This carboxyl group in aspartic acid or on glutamic acid can be attached to an amino group. When it is attached to an amino group, it forms an amide of that amino acid. So an amide of aspartic acid is called aspartate. An amide of glutamic acid is called a glutamine. The structures are here, and the formational attachment of the amino group is there, and we can see the formation of the carbonyl carbon after the attachment of the amino group. Then the next class of amino acids is basic amino acids. And we all know why these ones are called the acid amino acid, because of the acid group attached to it. And we have the basic amino acids, and we'll see why also they have Why are they called the basic amino acids? Yes? Somebody want to talk? Somebody want to talk?
No, sir.
Okay, right. So somebody raising hand. Okay, so the basic amino acid, for example, we have lysine. In lysine, we have the beta carbon, the gamma carbon, the lambda carbon, and the epsilon carbon. On the epsilon carbon, we have an amino group attached to the epsilon carbon. All these groups, the red, remember, is what we all call the R chain or the side chain or the R group problem. While in the case of arginine, we have the guanidino group. This group in red is what we call the guanidino group, where you have the methyl trimethyl group attached to a nitrogen, and then we have nitrogen bonded to carbon, double bonded to an amino group, and then it's also single bonded to an amino group. We call it a guanidino group. This is arginine. While in the case of histidine, we have an imidazole group attached to the alpha carbon. So all these groups now, they are basics because they have this amino group, and this amino group is basic in nature. That is why it has an additional amino group. They are basic in nature. So that is the reason why they are called basic amino acids. Then the next one is aromatic amino acid. Even from the name, we have just an aromatic group attached to it. The first one is benzene. So in benzene, sorry, the first one is phenylalanine. In phenylalanine, you have the beta carbon attached to a benzene ring or phenyl ring. While we already explained in the case of pyridine, we have the beta carbon then attached to a phenyl group or a benzene with a hydroxyl group. Well, the last one, we have a tryptophan, where we have an indole group attached to the alpha carbon. Then the last one, amino acids. This is the only amino acid that does not have the amino, or it has an amino group in form of amino, which form a ring structure we call pyrrolidine. So we have the pyrrolidine, in this case, even attached to first the alpha carbon, and then it forms a ring, including the amino, that is what makes the amino. So these amino acids, they are the ones that comes together, bonded by a type of bond we call a peptide bond, to form a protein. Do you have any question based on this? Do you have a question? Plus.
No, sir.
Yes, be so long.
I said no, sir.
Okay.
No, sir. No question, sir.
Okay. So you are getting everything?
Yes, sir.
Good. So, properties of amino acids. Some of the properties, there are so many properties, but briefly we talked about just a few of them, and both the physical and the chemical properties. The first one is solubility. There's a we are yet to talk about the amphoteric nature of amino acid, which I think is the next thing we talked about. But Yeah, one thing you know that all the amino acids ionize in a solution. So once it's ionized, can easily interact with water. Although the level of the degree of the interaction now depend on the nature of the R group. Some of them, the R group, also can ionize, now making the whole amino acids to be easily interact with water. Once it interacts, the more it interacts, then the higher the solubility. The lower the interaction, then the lower the solubility. Likewise, some amino acids have taste. Like some of them are sweet, very bitter. Some of them are even tasteless. We have the like of glycine, which we mentioned that the glycine is even named from glykos, which is a Greek word, which means sweet. We have alanine, we have valine, they all taste sweet. Some of them are tasteless, like we said. We have leucine, we have arginine and isoleucine that are bitter in taste. And there are even one that is being used as a flavoring agent, glutamate. Now, glutamate in form of monosodium glutamate has been used as a flavoring agent. And I think we all know this flavoring agent. We know Ajinomoto, right? Who knows Ajinomoto here? Can you raise up your hand if you know Ajinomoto? Just raise up your hand. You have ever used Ajinomoto? Can you raise up your hand? Plus, are you with us?
I don't even see where to raise the hand.
Sorry? Yeah, I can see somebody raising or Samui.
Maybe the person didn't know.
Okay, but do you know Ajinomoto? Just respond to me.
Yes, sir, we do.
Oh, good.
Yes, I will do.
And we know what we use it for.
Yes, sir. Yes, sir.
Right. Do we know the constituent, the active ingredient in Ajinomoto?
No, sir.
No, sir.
Some of you must have read it, I think, from this thing. It is an amino acid. It is an amino acid, glutamate. So the salt of glutamate in form of monosodium glutamate. You have only glutamate reacting with sodium to form monosodium glutamate. That made it to become a salt. So we have the salt of glutamate as monosodium glutamate, and it is used as flavoring agent. It has this flavor to give the taste, and a lot of amino acids also give this flavor and taste. Is that clear? Now, the next thing is light absorption. Some amino acids, most especially amino acids, they contain the aromatic ring like phenyl, alanine, tyrosine, tryptophan, absorb lights. So once you have a UV visible radiation, Veronica, why are you making noise? When you have a UV visible radiation at 280 wavelengths of 280 nanometer, this amino acid can absorb light. Then we have the formation of esters. The carboxyl group of this amino acid can easily react to form an ester, just like in monosodium glutamate. The monosodium glutamate is an ester of a glutamate, where you have the sodium reacting with the carboxyl group to form monosodium glutamate. They can also undergo the carboxylation reaction, where the carboxyl group is removed. So once the carboxyl group is removed, it's from a different compounds like a tyramine, like a histamine, like alpha aminobutyric acid, etc. We also have transamination reaction, where we have the removal of the amino group instead of the carboxyl group. While discussing metabolism, we'll definitely talk about some of this. Transamination is like taking away the amino group to another compound. In oxidative deamination involves the removal of the amino group, not transferring the amino acid to another molecule. So amino acid undergo all these reactions. So the amphoteric nature of amino acids. Do you have any question with regard to the properties of amino acid? So amino acids have the ability to donate or accept a proton. Now we say in a solution, when you have a solution of an amino acid ionize to form what we call a dipolar ion, meaning two groups will ionize, the carboxyl group and the amino group. That is why it is called dipolar ion or Zwitterion ion. Zwitterion or Zwitterions. Zwitter ion. Why is it called Zwitter ion? Because Zwitter means hybrid. So hybrid ion, meaning a compound containing both the positive and a negative group. So all these depend on the pH. Depend on the pH of the solution. At low pH, this is acidic pH. We have the carboxyl group remaining uncharged, while the amino group become protonated to form ammonium. So it will be ammonium positive with a positive charge. While at alkaline pH, you have the carboxyl group losing proton to become ionized, and then the amino group remain unionized in form of amino group. While at a particular pH we call isoelectric pH, the amino group will exist both in form of the deuterium ion, where you have the carboxyl group losing a proton, and then the amino group accepting a proton. So the carboxyl group will have a negative charge, and the amino group will have a positive charge. And that brought us to what we call the isoelectric points of pH or isoelectric pH. So what is this isoelectric pH? I've already explained this isoelectric pH. It's nothing but a pH at which the amino acid exists as a deuterium ion, a neutral ion. When we look back, let's see, a deuterium ion here, you have an ion, amino acid that contain a positive and a negative. So the positive and the negative can cancel each other, therefore making it to be a neutral ion. How does an amino acid become neutral? It is neutral at a particular pH we call isoelectric pH. And each of these amino acids differ in their own isoelectric pH. Or each amino acid have its own isoelectric pH. And that amino acid is neutral within that pH. Is that understood? Now let's look at the classical. How do you determine the isoelectric pH of this of an amino acid? We have so let me try it. See how can I wind up? We have this graph which shows the titration of amino acid glycine with pH. Increase in OH group causes the decrease in the pH. Remember, each group, now you have the amino group and you have the carboxyl group. Each of these groups have its own acid dissociation constant. And if you can remember the graph we gave, the earlier graph we gave while explaining the buffer, we saw it a pH equal to the pKa. That is a pH where a weak acid have its own evaporating capacity, where you have an equal concentration of the weak acid on the conjugate base. So when you have an increase in the concentration of in an amino acid, you reach that pKa of the when you continue, you reach a point where the pH will make the carboxyl group and the amino group to exist in ionized form. When they exist in ionized form, but the environment was made in such a way that for the carboxyl group, the environment is basic enough for it to release the proton to the environment. While for the amino group, the environment is acidic enough to accept a proton. At that pH, that is the pH, the carboxyl group will have a negative charge, and the amino group will have a positive charge. That pH is called the isoelectric pH. And at the isoelectric pH, the amino acid is neutral. Is that clear? Plus. Is the explanation clear? I took my time so that I'm a bit very slow so for you to be able to grasp what I'm trying to say. Did you get it? Lars, are you with me?
Yes, sir.
Yes, sir.
Alheri, are you with me?
Yes, I am.
Veronica, are you with me? Are we having network challenges?
It's breaking a little, but we can just little.
Network?
Yes, sir.
Yes, I do not work.
Okay. So let me briefly say it again. Now, when you have a solution of an amino acid, a particular amino acid, you determine the pH at which the amino acid or the solution become neutral. Or the amino acid become neutral. So how do you get the amino, the pH at which both the amino group and the carboxyl group will exist in form or will ionize in such a way that the charge will cancel each other. You know the strength of this, the tendency to accept. Somebody is making noise. The tendency to accept. Somebody is raising a hand or somewhere. Okay. The tendency to either accept a proton or to donate a proton differs between the two groups, the carboxyl group and the amino group. The pH at which that tendency equate to each other, that tendency became equal. Then the whole compound became neutral. The tendency to accept and the tendency to donate are equal. Then the compound became neutral. Is that clear?
Yes,
so
sir.
When you raise the pH, to the point that the carboxyl group find the environment basic enough to lose its proton. So it loses the proton. At that pH, also, the same pH, when the amino group also find the environment basic enough, so acidic enough to accept a proton, it accepts a proton and become ionized. So at that pH, the pH is called the isoelectric pH. Veronica, why is the noise coming from the side? Veronica, why is noise coming from your side? Okay, did we get that?
Yes, sir. So is it safe to say that that isoelectric pH is neutral because it's having the negative and the positive?
Yes, it's
So,
neutral. The
okay,
amino acid is neutral. So
neutral.
this yes, go ahead.
So the raising of the pH makes the carboxyl group able to release its proton, and that of the hydroxyl is it hydroxyl
The
or
amino group.
amino group now accepts the proton due to its lower pH. I
Yes.
don't know if I mixed it up there. All right.
Yes.
Thank you.
Yes. The due to the lower pH. Is it the pH lower enough for that to accept a proton? Is the pH higher enough for the carboxyl group to release a proton? So at that pH, that is enough for all of them to exist in ionized form. So that pH determine the pH at which the effect of the two can cancel each other. So you can see in the case of glycine, you have something in between the two because we have only two ionized group.